So, welcome to lecture series on advanced linear algebra. We have already discussed different types of linear transformations. Today, I will introduce another specific type of linear transformations which we are calling as a linear functional. So, what is linear functionals? Let V be a finite dimensional vector space. It is not necessary it has to be finite dimensional. Let me check V be a vector space over the field capital F. A function f from V to capital F is called as a linear functional from V to F or linear functional on V provided for any alpha and beta belongs to capital V and scalar C belongs to capital F, f of C alpha plus beta equal to C times f of alpha plus f of beta. So, this is the definition of basically linear transformations. So, small f is a linear transformation from V to F. Here this vector space is the field itself, that is W in our usual definition of a linear transformation T from V to W, here W equal to F only. So, this is basically definition of linear functionals. So, let us consider some examples. So, okay, consider capital V equal to space of n tuple f n over the field capital F. Consider n constants C1, C2, Cn belongs to capital F. Define a function capital F from V to F as for any element say alpha which is equal to say x1, x2, xn goes to sigma Ci xi I equal to 1 to n. So, I have defined a function from V to capital F like this. So, that is if I consider alpha equal to this ones, so it is like this thing please. So, f of alpha equal to C1 x1 plus C2 x2 plus Cn xn. We can quickly check whether this function is a linear transformation or not, or I mean to say the linear functional or not. For any other elements beta belongs to capital V and beta equal y1, y2 and yn, and alpha belongs to V, alpha equal to x1, x2, xn, C belongs to capital F, C alpha plus beta which is equal to C x1 plus y1 comma C xn plus yn type. So, it will be like this thing. Okay. So, f of C alpha plus beta will be equal to, according to this definition, I will have sigma C into your C into x I plus y I equal to 1 to n. So, this is equal to, one can rewrite C into sigma C I x I plus sigma your C I into y I equal to 1 to n, equal to 1 to n. So, this is equal to, I can write down C times f of alpha plus f of beta. So, this implies that f is a linear functional. So, now onwards I will write down L dot f, okay, linear functionals LF, okay, on vector space V, please. So, I can raise the question, what does this coefficient in star, if I define here, this is my say star. So, what does the coefficient in star, each coefficient in star represent? This is a question we can quickly answer by these things, please. So, consider B equal to, that is if I consider standard order basis, B equal to E1, E2 and En, where Ei equal to 0, 0, 1, 0, 0. This is ith coordinate is 1, all other coordinate equal to 0, please. So, this is my Ei. Then we have for alpha belongs to V, I will be able to express alpha in terms of E1, E2, En. So, if I do this, let alpha equal to your x1, x2, xn. So, I can write down this is equal to sigma di Ei. Then this is equal to basically I equal to 1 to n. This implies that di equal to xi, di equal to basically xi, please. So, alpha equal to sigma xi into Ei. So, T of alpha which is equal to sigma your xi into T of Ei, I equal to 1 to n. So, this implies Ci in star is basically T of Ei. So, Ci is basically the Ti. The image of here of course, one more thing here, this is not T, it is a F, please. Yeah, Ci is basically the F of Ei only. So, the image of T alpha I have written is equal to sigma Ci into xi, that. So, this Ci is basically the image of Ei. So, this implies we have written f of alpha equal to your f of Ei into xi, I equal to 1 to. Now, the question is it possible to generalize this concept for any finite dimensional vector space? I mean, one can write down, if a order basis is given to you, then is it possible that we can define the functions f like sigma f of Ei into xi form? Now, I will definitely answer these questions, but before going to answer this question, let me give some more examples of some more linear functionals, and then I will come to these questions. Okay. Let me consider second examples like this. Let V be all n cross n matrix over a field capital F. So, define a function f from V to capital F as, so this any element is a matrix A of the form n cross n matrix goes to, suppose, trace of A. This means that I am defining f of A equal to sigma your I equal to 1 to n. If I consider this is the definition of the function, then we can immediately check this function is also a linear transformation from V to F. I mean this function f is a linear functionals. Here we have for any A and B belongs to V and C belongs to capital F, f of C times A plus B, which is equal to, according to this ones, this will be equal to, I can write down, this is your sigma C into AII plus BII, I equal to 1 to n. So, this is equal to C into sigma AII plus sigma BII, I equal to 1 to n, I equal to 1 to n. So, this is nothing C into your f of A plus f of B. So, f is also a linear functional. So far I have taken example over the finite dimensional space. Now, let me consider couple of examples related to the infinite dimensional vector space. Let V be the space of all polynomial function from field F into F. So, this implies for P belongs to V implies there exists positive integer n belongs to set of natural number n such that P equal I equal to 0 to n. Which is equal to, basically I can write down P naught plus P1 into x plus P2 into x square plus Pn x to the power n. Consider a constant t belongs to capital F. Define a function f from V to capital F as P goes to P at t. So, this implies that f of P equal to P at t. So, if I define like this, then again we can cross check that f is also a linear transformation from V to F, or it is a linear functional from V to F, please. Linear functional from V into F. You can check it. So, this you can consider as a homework to check it whether F is a linear function or not. Okay. In mathematics, most of the times you use even standard examples. So, let me consider that ones. Say, let V be the space of all real valued continuous functions, continuous and real valued function on a closed interval, say a b. That is V equal to C a b. Okay. So, suppose this is my space. Define a function from V to F at L of g equal to a to b g of t dt. So, if I define this type of function capital L from V to capital F, so this is again you can check it is a linear functional and satisfy the definition of linear transformations. So, this is also because this integral is a linear operator. So, we can quickly check L of g1 plus g2 equal to L of g1 plus L of g2. L of c times g equal to c times L of g, that we can check it. Is also a linear functional on V, please, you can check it. Okay. So, we have seen couple of examples of linear functionals. Now, consider LVF, means collection of all linear functionals on V, that is collection of all linear functional on capital V. So, we know this is also vector space because it is a special case of LVW, which is also a vector space. And if dimension of capital V is finite, say n, then the dimension of LVF is also equal to n into 1 equal to n. In general, LVF we are denoting as a V star, which is called as dual space of vector space capital V. I mean V star is the dual of V, please. We can also cross check the concept of basis as we have seen in the case of LVW. Here also suppose if x on V is given, then and also basis in capital F is given, then also one can introduce a basis on LVF also. As we have seen that if you recall, while talking about the vector space LVW, when V is a vector space dimension n and W is a vector space dimension m, we have shown it that there are exactly mn number of linear transformation, that is EPQ, which are satisfying that. Suppose if you consider the basis of the capital V is say B consisting of alpha 1, alpha 2, alpha n, and if I consider B prime is the basis for the W consisting of say beta 1, beta 2, beta m, then we have defined EPQ. So, if you recall correctly, EPQ at alpha j is equal to, we have defined as a beta p if j is equal to q, other h is equal to 0. So, in that way we introduce the mn number of linear transformations. The same concept also holds good here. Now, only thing is that we have to find out what will be the corresponding appropriate linear functionals when a order basis on V is given to us. So, for this, so let us write down one small theorems. Let V be a finite dimensional vector space over a field say capital F. Let B equal to alpha 1 to alpha n be an order basis, an order basis of capital V. Then there exists an order basis B star consisting of F1, F2, Fn, that is set of linear functionals of V star such that Fi alpha j equal to delta ij, that is curve delta. So, this is equal to 1, I equal to j, 0 I not equal to j. Okay. Also, for any f belongs to V star, f equal to sigma f of alpha j and f j equal to 1 to n. So, any linear functional can be written as linear combination of f j with the coefficients as function value at alpha j, and for any alpha, alpha can be written as sigma your f j alpha into alpha j equal to 1 to n. Okay. So, let us give a proof. Okay. Given B equal to alpha 1, alpha 2, alpha n as an order basis of capital B. Consider B prime equal to singleton set 1. as basis of capital F. So, for each I equal to 1 to n, one can define a unique linear functionals Fi on capital V such that Fi alpha j equal to delta ij. One can define, or I can say that exist a unique linear functionals Fi such that Fi at alpha j equal to delta ij. I mean to say Fi at alpha I equal to 1 and Fi alpha j not equal to I equal to 0. So, this type of existence of linear transformation already you have proved it. So, I can give a guarantee that this type of linear functional exists. So, existence is guaranteed from the previous result please. So, one can say there are n such linear functionals on V such satisfying this type of condition please. It is basically same that EPQ, if you recall here P equal to 1, Q varying from 1 to n. So, my E1 Q or E1 I is my Fi. So, I hope this will be clear how one can say there exists a unique linear transformation or linear functionals Fi on V which will map alpha I to 1, all other elements to 0. So, there are n linear functionals. Claim this F1, F2, Fn is linearly independent. For any linear combinations, say C1 F1 plus C2 F2 plus Cn Fn, if I consider any f linear function which is linear combination of F1 to Fn, if I consider, I mean f equal like this which is equal to sigma Ci Fi, then we have, so we have f of alpha j is equal to sigma Ci and f of I alpha j, this one I equal to 1 to n. So, this is equal to, one can write down Ci and delta ij. So, this will be exactly equal to Cj. So, this implies if f equal to 0 implies that each Cj equal to 0. So, this implies that F1, F2, Fn is a linearly independent set of V star, and since dimension of V star equal to dimension of V which is equal to n implies the set, if I denote B star equal to F1, F2 and Fn, and then this is a basis of V star. So, here we have for f is equal to sigma C I F I, f of alpha j equal to sigma C I F I alpha j. So, I equal to 1 to n. So, what is this? This is equal to sigma, as I have written, C I delta I j. So, this is equal to simply C j. So, each coefficient C 1, C 2, C n are nothing f of alpha 1, alpha 2, f alpha n. This implies your the function f can be written as your f of alpha j into f j, j equal to 1 to n. Again, for any alpha belongs to V, for any alpha belongs to V, we have alpha, we can write down alpha as a linear combination basis element of V, that is alpha 1, alpha 2, alpha n. So, let alpha is equal to say sigma x j alpha j, j equal to 1 to n suppose. So, this implies that f I operating on alpha will be equal to how much? Sigma x j f I operating on alpha j, j equal to 1 to n. We know f I alpha j equal to delta I j. So, this is equal to sigma x j and delta I j, j equal to 1 to n. So, this is equal to simply x I. So, this implies the vector alpha can be written as sigma your f j alpha, alpha into alpha j. So, this implies coordinate matrix of alpha with respect to order basis B, which is equal to, I can write down f 1 of alpha, f 2 of alpha and f n of alpha transpose. This implies I can write down the coordinate matrix of f with respect to order basis B star, B star equal to, I have f of alpha 1, f of alpha 2, f of alpha n transpose. So, we have seen that any linear functionals can be written as a linear combination of this f 1 f 2 f n, where f 1 f 2 f n has been obtained based on the concept that given information that B equal to alpha 1, alpha 2, alpha n as an order basis for the B. We have seen here that if we consider the ith coordinate of that coordinate matrix, that f of alpha I mean function value at alpha I is the basically ith coordinate of the coordinate matrix of f with respect to order basis B star. Exactly same thing we have seen for the any vector alpha belongs to capital V, then the ith coordinate of the coordinate matrix of alpha with respect to order basis B is basically function value of linear functional f I at alpha. We shall make it more clear when we will consider more examples, which I am going to do in my next class please. Thank you.